Hi, we're going to practice calculating some Riemann sums for a given function f on a particular interval a to b. And just to remind everyone, a Riemann sum is formulated in this fashion. We have this index k that counts off n products, 1 to n, and those products are the height are areas of rectangles, where f of x bar sub k is the height of the kth rectangle, and delta x is the width of every rectangle. So this product is an area, and we're adding up in rectangles. We're going to formulate this 3 different ways. We might choose to evaluate f at the left endpoint of the subinterval, and if so, then x bar is a plus the difference k minus 1 times delta x. Or we might start over and choose the right endpoint of each subinterval, and then x bar for the kth subinterval would be a plus k times delta x. So that would be further along in the number line. Another way to formulate the Riemann sum is to choose the midpoint of the interval, and you see that it's similar in structure. It's a plus a difference times delta k, but instead of having the difference k minus 1 or the multiple k, we go right in between with k minus 1/2. It's between these two counters here. And later, when we want to add up these products, we can use our Texas Instrument calculator and use these commands, sum and sequence, which I find under the catalog menu. There are 4 arguments you have to type in: a function, an index, and then the lower bound and the upper bound for the number of terms. So just remember, when you use sum with parentheses, sequence with a set of parentheses, there's 1, 2, 3, 4 arguments separated by 3 commas. Okay, here's the problem we're going to do. We're going to calculate Riemann sums. We're going to do that 3 times. First with the left. We'll do the left Riemann sum, second the right Riemann sum, and we'll end up with the midpoint Riemann sum. Our function is going to be f of x equals x cubed plus 1. We're going to be on the interval 0 to 2. And I'm choosing to use 50 subintervals to approximate the area under the curve. Okay, so each time we do one of these sums, we need to take inventory. The interval a to b, a is 0, b is 2. How many subdivisions we're going to make. In this case, we're going to make 50. We choose our counter. We'll use a letter k as our counter in the sum. Then we need to make a calculation. What will be the width of each subinterval? Well, we take the difference of the endpoints, b minus a, and we divide by n. And in our case, this will reduce to 1 over 25, or we could use 0.04. The trickier part is to calculate an expression for x bar for the kth subinterval. And if you recall from our definition, we need to take a and add to that k minus 1, this difference, times delta x. You could also use the decimal there. And of course this will simplify. And then once we know what x bar is, we need to apply f to x bar. And our function, which is off the screen, but our function was x cubed plus 1. So we need to cube x bar and then add 1. So we need x bar, k minus 1 times 1/25 cubed plus 1. Our input cubed plus 1. And of course you can use your decimal there. Now to finish off the Riemann sum, we're going to sum k equals 1 to 50 areas of rectangles. We'll have the height of the rectangle times the width of the rectangle, delta x, which we already know. There's delta x. And up here above, we've written f of x bar, and we're going to need another set of parentheses. So we take k minus 1 times 1/25, that's cubed, and add 1. And when we start to simplify, then we have the sum times 1/25. That's how you set up the Riemann sum. Now, to make it a little bit nicer for typing into the calculator, we might want to do a little bit of distribution. Notice we have the difference cubed over 25 cubed times 1/25. So that's the difference cubed over 25 cubed times another factor of 1/25. So that'll put 25 to the 4th on the bottom. And then also we need to multiply the 1 by 1/25. So inside this big set of brackets is what we would end up having to type in to the calculator when we do sum sequence. And that would be the first thing we type in, and then we tell the calculator the index and that we're summing from 1 to 50. Okay. If you want to try that, I can let you know what the results should be. If you let the calculator give you a fractional answer, that fraction will simplify to 3,651 over 625, and that is approximately 5.8416. Or it's exactly that. Okay. Now let's switch over to the left. See, this was the left Riemann sum, excuse me. The left Riemann sum because of the k minus 1. Let's take that same function. Okay. Let's take that same function. Excuse me, I've got too many pieces of paper going on here. Same function on the same interval, 0 to 2, 50 subinterval, k is our counter, delta x is still 2 minus 0 over 50, or 1/25, and we'll do the right Riemann sum. What changes is how we formulate x bar. We still start with a, but now we add k copies of delta x. And so this time we simply have k over 25. Okay. When we plug that into f, remember f of x was x cubed plus 1 for our example. When we plug that into f, we have our fraction cubed plus 1. So we're going to get k cubed over 25 cubed plus 1. And now we can sum that up. K equals 1 to 50. We have the height of our rectangle right here. K cubed over 25 cubed plus 1 times delta x. That is our right Riemann sum. And it could be simplified a little bit before we type that into the calculator. And we distribute the 1/25. We get k cubed over 25 to the 4th plus 1 over 25. And again, this whole thing would be the function. K is your counter, and you would run that counter from 1 to 50. Okay. If you'd like to pause, get that typed into the calculator, and then check it. The right Riemann sum has a value of 3851 over 625, and that's approximately 6.1616. Okay. And to finish the 3 different approximations, we're going to make similar calculations one more time. Let me put in a new page. Okay. Again, our function is still x cubed. Pardon me. X cubed plus 1. That hasn't changed. We're still on the interval 0 to 2. We're going to use 50 subintervals, and delta x hasn't changed. What changes in each different formulation is how we choose x bar. We always start with a, and we're going to add copies of delta x, but this time we're going to use the difference k minus 1/2 times delta x so that we pick up the midpoint of each subinterval. Okay, when we apply f, we're going to take our input, 0 doesn't matter. Let's rewrite that. 0 plus k minus 1/2 times 1/25. And now we take that input and we will cube that and add 1. Okay, and like before, we'll get the difference cubed over 25 cubed plus 1 as the height of the rectangle. And for the final step, now we add up the 50 terms. We take the height of the rectangle, the difference cubed over 25 cubed plus 1. That's our height. And we take it times the width, which is up here at delta x. Okay. That is our midpoint Riemann sum. And if we wanted to, we could distribute the 1/25th through this binomial before typing it in. This would be a good place to pause if you want to go ahead and do those calculations on your technology one more time. But the value of the midpoint Riemann sum, 7,499 over 1250. It's very close to 6, but it's closer to 5.9992. So that was a calculation intense example. But that is our first example of a left, right, and midpoint Riemann sum for the same function on a given closed interval.